Hey, it's Matthew Todd and welcome to lesson 3 in this module. In this lesson, I want to show you a demonstration of TDD. I want to take a very simple application and show you what adding the first couple of features to this application in a test-driven way would look like. Now I know that some of you may have some experience of TDD already, some more than others, but even with experienced developers, I find when I run this course in person, they always get something out of this. There are always a few surprises for them. I'll show you a fairly purist demonstration of TDD. I think it's useful to show what it would look like in its purest form, and sometimes it is useful to take things at this such a low level of detail, other times not so much, but it's always good to know what it should look like in its pure form, so that when we do take shortcuts and try and do things in slightly bigger chunks, we know exactly why we're doing it. So, with that in mind, the application I want to demonstrate today is one I often use as an exercise, which is the reverse Polish notation calculator. So with a reverse Polish notation calculator, the operator follows the operand. So rather than 1 plus 2 for addition, it would be 1, 2, plus. And as you can see from this demonstration, the calculator is a stack-based one. So we can put multiple values on the stack, like so, and then apply the operators. And we can see the stack is manipulated, values being taken from the stack, and as we perform a calculation, the result of that calculation is then put on top of the stack. So in this example, you can see the top two numbers are taken from the stack, 3 and 2. We perform the add operation, and now we're left with the first value of 1, and the result of that calculation, 5 on the stack. So we've now got two numbers on the stack, and you can see here we can apply another operation again, replacing those numbers with the result of that calculation. If you're on a Mac like I am here, the built-in calculator application has a reverse Polish mode which you can put it into. But there are many calculators you can download or even use online which will let you play around with the reverse Polish notation. The Wikipedia page, as you can see here, also has a good description of what reverse Polish notation is, as well as a table which gives some sample calculations, showing how the stack is manipulated as the operators are applied. Now in this particular video, I'm going to TDD a very basic form of the calculator, initially just supporting the add operation. And in this video, it's going to be in Java. If you prefer JavaScript instead, prefer to see a JavaScript demonstration, then this exact same exercise I've repeated in JavaScript, and you can see that in the additional resources section on this page. So here we've got a standard JavaScript project, no source files at the moment, and if we look at the package.json, we can see we've got a couple of dependencies needed for testing. So we're going to be using Mocha as the test framework, and the chai library to make assertions. I'm using Visual Studio Code, obviously you could use whichever editor you wanted. Visual Studio Code does have some nice extensions like the TDD one, which will automatically run our tests every time we save a file. So we're taking a test-driven approach, so we'll start with the test code. We'll simply pull in import for chai. And we need a calculator to test, so we'll require it like so. We're going to be using the should style of assertions, hence the chai should call. Obviously you can use whichever style you prefer. So starting with the simplest thing we could test, the simplest thing to test will be a new calculator, thinking about how that behaves. So if we describe a new calculator, well, what's the simplest piece of behaviour we could verify about a new calculator? Well, we know the RPN calculator is stat-based. The simplest thing we can say is that a new calculator should have an empty stack. So we'll add a test method, like so. So it should have an empty stack when just created. Now if we save our test so far, we can see that it's failing. And that's because our calculator file, source index, doesn't exist. So let's create a simple calculator class here, so this passes. Okay, so our test is now passing. We've got a calculator class, so our test is being loaded and running at least, but we're not making any assertions yet. So what do we want to assert? So we want to ensure a calculator has a stack, and that stack is empty. Now thinking about how we want to represent our stack, we'll represent our stack as a simple array. So when we attempt to retrieve a stack from a new calculator, we would expect this to be equal to an empty array, like so. Now saving our test, we can see it fails as we expect. It's failing because calculator.stack is not a property that exists. So what we're going to do now is switch to our implementation and add an accessor method returning something. In this case, we'll return the simplest thing possible to make the test pass, so just an empty array. And you can see saving this, our test is now passing. So now we can move on to a next test, allowing us to build out some more functionality. So thinking about our stack still, we would expect our stack to have a size of 1 after pushing a new value. We can't add any operations yet because we haven't got any values to operate on. So our calculator needs to support pushing new values onto the stack. And the simplest test we could possibly add for this is relating to the stack size after pushing a new value. So adding a test in the same way before. Instantiate our calculator. This time we're attempting to push a value. And we're asserting that the stack has a length of 1. And this is failing because push is not a function our calculator exposes. So going back to our implementation, we can now try and make this test pass. So it's only at this stage we're actually forced to store a stack within our calculator. So we'll add a constructor, initializing our stack field to an empty array, changing the getStack to return that array, and now we can look at our push method. So here we're just pushing a default value of 0, going for the simplest implementation possible to make the test pass. And you can see saving that change, our test is now passing. And it might seem overly contrived to add an implementation we know isn't the final implementation, but we're following a TDD approach, iterating rapidly between test implementation, ensuring that all the behaviour we care about is tested, which is why we're only going with enough implementation as needed to pass the test. If we want to make this implementation more complex, we should add some test code first, which is going to exercise that behaviour. So on to our next test. Let's add a test to ensure the value that's on the stack after calling push is the value that we requested is pushed onto the stack. So as before, instantiate the calculator, push a value. This time we're making sure that the value on the stack is the value that we pushed. And we can see after saving this, our test is failing as we would expect. So now switching back to implementation again, let's change our push implementation to make this test pass. So let's add a parameter to our push function and push that value onto the stack. So simple change, but again taking a test-driven approach, rapidly switching between test, implementation, going from red, green. So now let's think about our next test. Well, a behaviour that we care about is what happens if we attempt to push more than one value onto the stack. Whilst we think from a simple implementation it should work, let's add a test to ensure this is behaving as we'd expect. So this time we're creating a new describe block because our calculator is starting from a different precondition. This time we're interested in describing what happens to a calculator that's already got a value on the stack. So here we've got a before each block, which is setting up a new calculator, pushing a value, so that every test within this section will start from that state. And let's create a test to ensure that when we push another value onto the stack, the calculator returns the stack with those two values in the correct order. So in this case in our test we just push another value, and then we add an assertion to ensure that the stack contains both those two values in the right order. And we can see, saving this, our new test is passing. Now, whilst not strictly red, green, not following the purest TDD approach, it is an important piece of behaviour that we care about, and we're adding this test to ensure we've got confidence in our code to ensure that it is behaving as we would expect. And whilst we probably could have come up with an implementation that would have passed the previous test, but not this one, I think that would have probably been too contrived. Now before moving on with additional tests, let's just do a quick refactor. This is some of our test code rather than the application code, just to make use of the before each block in our first describe section. This will save each test having to instantiate the calculator itself. Each describe block is going to be giving us a calculator in the right state to test. Okay, so now we've got a calculator with a stack we know we can manipulate. We've got enough tests and implementation that are going to put us in a state where we can start to think about the add operation. But before we jump in to the actual calculation itself, let's think about what an add operation should do with an empty calculator. Well, the add operation needs two values to operate on. We're adding two numbers, so we need there to be two numbers on the stack. Let's first add a test describing the behaviour where we attempt to invoke the add operation when there are no values on the stack. So with a new calculator, it should not allow the add operation when no values have been pushed onto the stack. So adding a test for this. We've already got a calculator with no values on the stack. And the way we'll indicate that this is an allowed operation is we'll throw an error when this is attempted. So in our test, we'll use should, because we're using that style of assertions, and we'll say should throw an error when calculator.add is called. Now you can see this test is failing currently because expecting undefined to be a function, because our add function does not exist on our calculator instance. So let's add a very simple implementation. So if we just leave that implementation blank for now, we can see that our error message is different. Our test is still failing, but it's now failing because we're not throwing an error rather than that function not existing. So now sticking with the implementation, let's have the simplest implementation possible in order to make that test pass, which is simply throwing an error. And on saving that change, you can see our test is now passing as we expect. Okay, we said an add operation needs two values to operate on, so we'd also expect an error to be thrown if the calculator only has a single value on the stack. So we've already got a describe block which describes a calculator in that state, so let's add a new test here to ensure the add operation does not allow when no other values have been pushed onto the stack. So there's only a single value. And the assertion is exactly the same as our previous test. Now we know from the implementation that we've got, we always throw the error, and as we can see, this test is passing. So here we don't actually have a failing test first, because our implementation is so simple, but it's an important test to add because this is key behaviour that we care about. And as we make the implementation more complex, this is a bit of behaviour that we want to ensure is preserved. So now we know the add operation can't be invoked if there are no values on the stack, or if there is one value on the stack. How about if there are two values on the stack? Well, if there are two values on the stack, and we attempt to invoke the add operation, we'd expect it to succeed. We would expect the stack to have been manipulated so that there's only one value on the stack now. So we'll create a new describe block for this because our preconditions are different. We want to start with a calculator with two values on the stack. So with a before each block as before, creating a new calculator. This time we're pushing two values rather than one value onto the stack. And now we can add our test to ensure that the stack should have a single value after applying the add operation. So previously there should be two values. After calling add, there should only be a single value. And notice we're not testing everything about the add operation result here. Here we're testing one piece of behaviour, which is that the stack has been manipulated such that there's only one item left on it. So we invoke add, the calculator stack should have a length of 1. And we can see this fails as we expect because we're always throwing an error from this add method, from this add function. So switching back to our implementation, let's add the simplest implementation we can, which will ensure that all of the existing tests will pass. So we'll check the stack length. If it's less than 2, we'll throw an error. Otherwise, we'll simply remove a value from the stack. Whilst not the correct implementation we'll end up with, it's enough to make the current test pass. So now that this is passing, what about the result of the add operation? Well, after calling add, we'd expect there to be one item on the stack, but we'd also expect that value to be the result of performing the addition. So now we can add a test to ensure that the stack contains the correct result of the calculation when we call add. So as before, we'll call calculator.add in our test, but this time the assertion is different. We're making sure that the value at the top of the stack is the result of the addition, so in this case 5 plus 2, which is 7. Now, as we would expect, this test is failing because we're not actually performing the calculation. Here we're just removing a value from the stack, rather than removing two values, performing the calculation and pushing the result onto the stack. So switching back to our implementation code again, let's change this to remove two values, like so. Now perform the calculation, pushing the result of that calculation onto the stack. And you can see saving this, all of our tests are now passing. So we've taken a test-driven approach to creating a very simple stack-based calculator that supports the add operation.